Sorry for the delay with the technical problems. Okay, so, well, it's a pleasure to introduce you Pierre Cox. Pierre Cox is the director of IRAM, one of the most important ground-based installation in the gigahertz range. And, well, for me it's a pleasure. I know Pierre since more than 15 years ago, where he was more focused on planetary nebula and latest stages of stellar evolution. Now he shifts his interest to the early universe, and, well, that's what he's going to talk about today. He got his PhD at Paris Meudon and got a postdoc at the Max Planck Institute in Bonn, and later got a CNR's position, and as I said, now is the director of IRAM. So,
thank you. Okay, that's working. Okay, so I'm all wired. And so first of all, I would like to thank you, Paco, for inviting me here. It's a pleasure to be here. I think I've never been to this institute. I've been to Tenerife, but to the other part of the island. And so it's a real pleasure to discover the institute, but also the surroundings. I walked around in Laguna yesterday, and I was really amazed how beautiful it is. It's a real pleasure to be here. It's also a pleasure to be able to talk about IRAM and to present what IRAM is and what IRAM has done over the past few years in the field of the studies of galaxies and quasars at high redshift in the early universe. And then I will also take the opportunity of this talk to sketch the future prospects for IRAM, because we are in a completely new area since ALMA is taking off and is being built and will very soon be operational. And so we're not the best ones as we were for 30 years, but now we have to find ways of squeezing in good ideas to still survive in the shadow of the giant called ALMA. And so my talk is divided in essentially 3 parts. As I'm the director of IRAM, I think it's polite at least to introduce what IRAM is and what IRAM does. IRAM is also an international endeavor between Germany, France, but also Spain. It's a Spanish institute. It is located in France, the headquarters, and our mission is to operate 2 main telescopes. One of them is in France, on the Plateau de Bure. It's an interferometer. The other one is in Canada, in Spain, and it's the 30-meter telescope. So the second part I will briefly introduce, because I don't know what the background of most of the people here, why millimeter studies are vital in probing the early universe. I'll make a few general comments, and I'll go quickly on that, and I will then present the results which recently were obtained with the IRAM telescopes. And essentially I will concentrate on very recent results, which are follow-up ground-based observations of the Herschel discoveries and the uncovering of many incredibly interesting sources. And then I will finish with the future in NOEMA and so the ALMA area. So IRAM is 30 years old, and 30 years ago, both at the Plateau de Bure and Pico Veleta, on top of the mountains, you see that there are things on the sort of like a maintenance hole on the Pico Veleta, and on the Plateau de Bure there was nothing except astronomers enjoying the winter sun whenever it was there. And 30 years later, this is the 30-meter and the Plateau de Bure. So the Plateau de Bure is a interferometer with 6 telescopes, antennas of 15 meters diameter, which are now spreading over 800 meters in baseline. And the 30-meter is a D-prime dish, working at and most sentiment of its type. So I think one of the keys of the successes of IRAM is that there has been an ongoing gradual enhancement at both facilities, which led to more and more powerful instruments. And I think the key to this is that everything is done in-house. I mean, from the telescope, the panel conceptions, down to the electronic, the fast electronic, the receivers. Everything is really done at the Institute. And since the Institute is a small institute, they're typically about 120 people, there's a flexibility in reacting to whatever is available on the market, on technology, and then improve what we offer to the community. We also have a very stable budget since 30 years, and that is also a key to the success. So I think there are three words, key buzzwords, which are the combination of which make the success of IRAM. It's flexibility, sensitivity, and frequency coverage for all three instruments. And the range of angular resolution goes from 30 arc seconds for a single dish, now down to 0.2 arc seconds and even 0.15 arc seconds for the highest frequencies with the interferometer. Of course, the other ingredient in the success of IRAM is the excellence of the people working there. And just for information, about 80% of the people are engineers, technicians, operators, and they're really the top leaders in their field. So the Plateau de Bure has undergone over the last 5 years a complete change, and in fact it's a new instrument as compared about 6 years ago. New because, first of all, in 2005 we extended the baselines. We doubled both the east, west, and the north-south baselines. So you have an aerial view here of the array in its highest configuration during the winter. And then we changed completely all the receivers on 6 antennas over a period of extending over 4 years, adding 2 new frequency bands which were never available before at 2 millimeters and recently at 0.8 millimeters, so 150 gigahertz and 350 gigahertz. We replaced backend, so we have a new backend since last year, and over the last 2 years we replaced for 4 of the antennas the entire set of panels, going from carbon fiber to aluminum panels because they are much more stable and they allow you to have a less maintenance and a greater stability and also a better pointing and a better efficiency, which is very important for the higher frequency. So the baselines at the Plateau de Bure, there are essentially 4 configurations, a compact one, which gives you at the lower frequencies a angular resolution of about 6 arc seconds. And then you go to steps of 4 different configurations up to the biggest one, which is shown here, which achieves for, that's a so-called A configuration for the highest frequency this winter. We observed at 370 gigahertz and achieved 0.1 arc second. So we're doing really ALMA science, essentially. The receivers which were replaced as compared to the old receivers allowed to make a gigantic step forward in sensitivity by factors of many, up to 10 or 20 or so in the continuum, as you can see. And this is because they are really outstanding state-of-the-art receivers. And also the bandwidths of these receivers are wide and cover 4 gigahertz. And you see that there are also 2 new windows at 2 millimeter and recently installed 0.8 millimeter. Just to give you an example of the combination of the high sensitivity receivers with the correlator, those are 2 examples. One at the left here is a H2 region. It's a spectral survey over 4 gigahertz. And the right is a spectral survey, but done in a quasar, which is at the redshift of 2.3, I think. Both spectra were taken 10 minutes. And you see that there's a wealth of data in the H2 region, many, many lines, so that's really doing 3D chemistry. And for the high-Z quasar, not only do we see the very strong CO line, which you see at the left of the panel, but you also see other species, molecular species, which pop up immediately in about 15 minutes because of the sensitivity. So the combination of the new correlator, the new receivers, open up a complete new window in the probing whatever from the galactic H2 regions out to the highest Z known objects in the universe. Another example, I show this because Arturo is in the room and it's my old interest as well. This is a spectrum of a well-known protoplanetary nebula here on 618. That's the first spectrum we took at 350 gigahertz in last December. It was the first test. It worked fantastically, and that was only done in 3 minutes. And you see that the spectrum covers not only large bandwidths, but it's a full width. I mean, there's a full wealth of data and spectra and molecular emission lines, which are seen here. Briefly on the 30 meter. The 30 meter has 2 types of instruments. There we also made considerable changes. First of all, there are sort of multi-pixel instruments, both heterodyne. There is a camera operating at 1 millimeter called Hera. And then there's a bolometer, which is doing a lot of work, especially the high-Z work, to find out the dust emission in the quasars and the galaxies in the early universe. A couple of years ago, we changed all the receivers also at the 30 meter, replacing the old receivers by a new type technology receivers, basically an outspring of what was done for ALMA. And we changed all the receivers, including a new band operating at 350 gigahertz, also at a 30 meter, which is fully accessible to the community. You see that it's not easy to bring sometimes receivers to the telescope, and there we had to use a helicopter because of the snow at that time. The receivers are really state-of-the-art. For the 350 and the 100 gigahertz receivers, there are two SB receivers covering 8 gigahertz, and for the 3 millimeter receiver, and they all have 4 gigahertz bandwidth. The aim in the next coming years is that all the bands will have 8 gigahertz bandwidth, so that you can cover in one go in a few minutes, in fact, the whole window available to you, either at 3, 2, 1, or 0.8 millimeter. And as an example, this is a spectrum of Orion, the full spectrum in the 3 millimeter window, which was taken, I think, in 10 minutes. And it really shows you the power of probing at once all the spectral richness of that type of objects. They are also opening a new window in the work, especially for the galactic H2 regions and star-forming regions. So now let me go to the second part of my talk. And of course, the combination of sensitivity, flexibility, and wonderfulness of the correlators immediately translates to a success in detecting sources which are extremely weak. And this is a sort of a hunting result. I haven't updated it over the winter. I mean, it would be interesting to do that, but I didn't have the time. But I think that's a good illustration. It shows you all the robust detections in molecular gas in objects which are at a redshift greater than 1. And everything which is red was done by IRAM. So you see that the field is absolutely dominated by IRAM, simply because, for the time being, IRAM is the most sensitive instrument around, and these things are very difficult to measure. The thing will, of course, change with ALMA. Will come into the play. And I think that we'll be in an equal competition here on the ground. But still, I think that's quite an impressive result. So let me briefly tell you why millimeter radiation is such a key player in the understanding of the physical properties and also the chemical properties of objects which are in the early universe. So just this is a sketch of the history of the universe, where you see in redshift here and in time on the left. You see that essentially what we are probing now is something around the so-called epoch of reionization, when the first stars and the first quasars and galaxies were formed and reionized the hydrogen around them. And actually we are probing up to redshifts of 7 now, and looking for molecular gas up to these redshifts. So well into the reionization epoch. And then, of course, the major studies are concentrated on the time scale between, let's say, 2 and 4 in redshift, where the major part of the mass buildup started and where the quasars in particular had their peak in activity. So this is just to give you an idea about where we are probing. And the probe into the reionization epoch is pretty new. It's about 5 or 6 years ago, and more we have more and more objects. And hence we understand better what type of objects they were and what their conditions were. So let me skip this one. Just a brief overview over the quite interesting history of the so-called infrared luminous galaxies. I think it's one of the tremendous heritages of ARAS, who did find these infrared luminous galaxies, where essentially most of the luminosity is radiated into the infrared and not in the optical, simply because they're infrared by dust, and the dust just absorbs the light of the stars which are formed there. Also, these objects are very active and are known to form stars at a tremendous rate, in excess of 10 up to 100, or even sometimes thousands solar masses per year. So in the 90s, there has been a flurry of activity. Essentially, was the discovery of CO in one of the ERAS sources, RS 10214, and that triggered the whole field, essentially. And all the interferometers really looked to these objects, and with success. At the beginning, it was very slow, but now we have a pace which is quite impressive. And from the mid-90s onward, There were more and more work done by bolometers, further detections of molecular gas. And there was one very difficult task was to determine the distance to these objects, which were found in deep fields done with bolometer cameras. First of all, you have to identify what the optical counterpart is. Sometimes there is no optical counterpart because it's completely enshrouded in dust. And it's very difficult, it's renowned to be difficult to find the redshift of the object. One ideal way to do that, and we are currently going into that area, is to directly measure it without optical or UV with the millimeter CO lines. So doing broadband search of a CO line, and then you will find the redshift. And I will show you one example which was a success recently. Of course, today there is many things. Spitzer has done its work, but Herschel is in full flurry and completely changed, I think, the landscape. And tomorrow the landscape will be changed again with the upcoming from ALMA, NOEMA, which is the project I'm going to talk about, and another project like CCAP. So we're really living into a time which is quite interesting and enthusiastic. Just as a reminder, the antenna galaxy everybody knows about. In fact, if you only look at the optical picture, you're missing about half of the story, because the actual activity of the star formation takes place into the most enshrouded dust parts of the galaxy, which are invisible in the optical wavelengths. And to have a full view, as you can see here in the CO emission, a full view of the galaxy and an understanding of the star formation history in that galaxy, you need both the optical, the UV, but also the millimeter tracing both the dust and the molecular gas tracing. It's just a little field guide of what you expect in a spectrum of a luminous infrared galaxy. So this is a model. What you essentially see is a strong continuum, which is normally peaking, depending on the dust, at wavelengths around 100 microns or so, between 100 and 200 microns. And then dominating that continuum emission of the dust, you see a series of lines, which are due to the series of rotational lines of carbon monoxide, CO, but also the fine structure lines, the atomic fine structure lines like C+, like oxygen, like nitrogen, which are dominating the cooling of the gas. And all these lines are, you see for the CO, the lowest ones are emitted at 3 millimeter. The 3 and the 2 and the 1 millimeter band the 3, 1, and 0.8 millimeter band are wonderful because the CO transitions, the low ones, fall into these bands. So another interesting thing for the millimeter things. But all the other CO lines up to 10 to 9 or whatever are all in the far infrared. So the major part of the infrared, the lines are really in the far infrared regime. Let me skip. Just as a reminder, when we say luminous infrared galaxies, they are indeed very luminous, and they are all in excess of 10 to the 10 solar luminosities. So they are really monsters. This is a important plot. This is a better quality thing, which shows you that when you're looking in the distant universe, of course, you're losing flux because of the distance, and it goes to the square of the distance. But there's a so-called inverse K correction, whereby the more you move, the thing is shifted. Of course, it's redshifted. But then if you look in a millimeter, what happens is that you lose, of course, in flux, but you gain because the peak is shifted into the window. And it's done in such a way that, for instance, for a given luminosity, you see that independent of the redshift from, let's say, 1 to 10 or so, the flux you measure is absolutely independent of the measure of the redshift. So you have a fantastic tool here to probe up to redshifts of 10 with the same sensitivity a given galaxy for a given luminosity. And this is simply due to the fact that the peak is shifted gradually into the millimeter window. So that's the first point, why the millimeter windows are so important. There's a second, that's for the dust continuum emission. There's a second effect which is less pronounced but still existing also for the CO lines. So the CO lines are shifted into the window, and also you have this K correction for the CO lines. The other trick of nature which helps a lot, and I will talk about it quite a lot, is the gravitational amplification. The more you go in depth into the universe, the more likely it is that you are encountering a massive galaxy in between the line of, the observer and the distant object. And then you have the so-called gravitational amplification, where the image source, the source is distorted and amplified by huge factors up to 50 or so, 30, 50. So and that enables you to probe objects which are very weak, you wouldn't see normally with the current instrumentation, But because of the amplification, you can detect them. And because of the distortion and the sort of expansion of the image on the plane of the sky, you can see details you wouldn't be able to see otherwise. And so you can really probe up to scales of galactic, giant molecular clouds at distances of redshift of 4 or so. And I will show you some examples. So the activity of detecting such galaxies was essentially doing bolometer work, so deep fields, was really booming in the 90s and the early 2000s. The problem is that many sources were found, many hundreds or so, but only a handful of them were identified in their distance because nobody knew the redshift of these sources. That was a very, very difficult exercise. There was a breakthrough done by Chapman using the Keck instrument telescope, doing very deep UV spectroscopy and finding weak lines which enabled them to follow up in other telescopes to find the molecular dust and molecular gas. This has completely changed with Herschel. I mean, Herschel is, I think, a spectacular success, and I see somebody who is very well aware of this here. And I choose to show you a result which is already old, but gives you a prospect of what Herschel is impacting in that field. This is an image of good North. It's, I think, in the Hermes program, where you see a combination done with the Spire instrument. So it's a photometer working at 250, 350, and 500 microns. And the combination here, you see it's a web and a sort of zoo of different sources. Every point you see here is indeed a galaxy. And what is interesting is that if you show at the same scale, the SCUBA Hubble deep field, which was really the sort of Rosetta Stone for a long time for the studies in the high Z universe, that was done with excellent weather over many nights with SCUBA. I don't know how much time this took, but probably about an hour or two or so. And so you see we are entering a completely different realm. It has nothing to do anymore. And there are gazillions of sources to be followed up from the ground. To give you an idea how many sources there are, so the quality of the data is very well. Here you see a famous cluster, Able 2218, with the different images. Of course, 250 micron has the best spatial resolution. But this is the numbers of December 2009. You see that even if only part of the survey was done, already there were something like over 25,000 sources identified. And now it must be in the 100,000s, I think, at least. So there's a huge catalog which is now floating around with fluxes which are really big fluxes, about 20 millijansky or so at 250 microns, which is available to do follow-up observations. So I think that as of today, as we speak, there is really a completely new area which has been opened and which has been really, so far I know, unexplored yet. And everything we have done is the tip of the iceberg, and it's quite fantastic. That's what I would like to talk about now. So that is only 7% of the total Hermes time. And Hermes is only one project. There are other ones like Atlas. So let me now go to a series of illustrations of studies which were done aimed at understanding the physics and the conditions of the gas out of which stars are formed, which are surrounding either black holes at a very high redshift or starburst galaxies. So here is a summary of work which was done trying to find molecular gas and dust emission in quasars at redshifts greater than 6. So they are really probing the reionization zone. All these quasars were found with the SDSS, with the Sloan survey. And so it's a very nice combination of work, collaboration between people of the SDSS, the optical people, and people working either in the radio or in the millimeter wavelengths. Up to now, I think there are 8 of the, or now 10 of the brightest millimeter quasars have been detected in CO at redshift of 6. There are about now 15 quasars above 6 which have been detected in the dust. And so it's a very high detection rate, and you see some of the examples here. You see how weak the lines are. This line, which is here in CO, is less than 1 millijansky, and it was observed in about 4 hours or so. So they're really robust detections. There's a map here to the right. It is unresolved. And typically, the gas masses around these objects are in excess of 10 to the 10 solar masses. and with CO luminosity also in excess of 10 to the 10. One of the quasars, which is still the farthest away for which we do have information about the gas properties, is G1148 at a redshift of 6.4. The image here is the optical image where you see the little red dot, which is only seen in the Z band. Everything else below that is undetectable. And you see here a nice result of the VLA where we have mapped the CO322 and resolved it in a sort of extended emission around the quasar, the black hole being really the center of this emission here. There also the gas is in excess of 10 to the 10, and the dynamical mass has been estimated about something like 510 to the 10 solar masses. So this is an interesting combination of data because it allows you to, when you map the source, and to derive the dynamical mass, which is a very important parameter in theory, but also to compare it with the mass of the black hole and see if their relation, which is found locally, is also seen when these objects were formed. Okay, this is also a nice example of a source for which we successfully detected the C+ emission. The C+ emission line is emitted at 1 terahertz at 158 micron, and it's shifted here in the band at 1 millimeter in the ground. So you're doing from the ground what is very, very difficult to do, which, you know, C+ was a very difficult thing to do. Now Herschel does it, of course, with PAX and also Hi-Fi. But we do it from the ground. It's easier. So that's one example. The spectrum here was done only in 3 hours in the D configuration, and also we mapped the C+ emission, and it's compatible with what you see in the CO. C+ is an important species to probe because it carries the essential cooling of the interstellar gas in galaxies. I will come back to the C+ later on. So those are were for the quasars at high redshift. So sometimes astronomers are lucky, and you have serendipitous detections, people looking for something and finding something completely different. I'm going to show you 2 examples because the 2 examples are quite spectacular. The first one is the so-called eyelash, where people did a deep field somewhere, and suddenly there was this huge source, which you see here, popping up, with a flux at 350 gigahertz of something like 30 millijansky. And it was completely unexpected. Nobody knew what it was. As you see here in the optical, nothing is seen at the barycenter of the isophone there. And you really have to go to the near-infrared to begin to see something. This is a nice example of a detection of CO blindly with one of the instruments which is now currently available here on the Green Bank telescope, which is a low spectral resolution spectrometer covering a huge bandwidth, so about 20 gigahertz or so. And you see that they did that here, and they detected the CO line, which is the CO1 to 0. We got a phone call at the Plateau de Bure, immediately looked at another line and detected a very strong line here, which is the transition CO322. This is one of the strongest objects ever measured, both at the Plateau de Bure, at the GBT, and with the 30 meter. It's quite an exceptional thing. And we followed that up with the SMA, which is an interferometer in Hawaii. And this is an image in the continuum, not in the CO line, where you see that this galaxy, in fact, what you're measuring is a sort of stream of clumps, elongated along one direction. And clearly what you see here is an amplified object where the criterion line in this paper, this is a paper in Nature, is here. And you see symmetrically around it the images, the source image of this amplified and distorted object. So here, what is quite amazing is that you can probe with going back into the source plane and correcting with a sort of model. You can probe up to 100 parsecs for an object which is at the distance of a redshift of 2.3. So that's the beauty of the amplification. There are not many of that sources. Let me go a little bit. So it's so strong that we did a full study of the CO lines with the 30 meter and the Plateau de Bure. As you see to the right here, I don't know if you're familiar with this, but this is an energy diagram of the CO lines and the various rotational levels. And you can derive from this quite interesting and constrain the physical condition of the molecular gas. So you see here there's a wealth of measurements from CO1 to 0 up to CO, I think it was 12 to 11 or so. Those lines are emitted also in the TRS region. And you can model that, and you can derive conditions for the gas. You see it's about 10 to the 4 centimeters minus 2. It's very dense. It's very warm, 50 K. And the mass corresponding to that is about in excess, again, of 10 to the 10. So we measured that with the Plateau de Bure, not in the continuum, but there in the CO lines. We also have had the continuum, of course. And here is a better view of what is happening. This is the image obtained in the A configuration with about 1 arc second, or 2, what is it now, 0.3 arc seconds, where you see again that it's completely symmetric with respect to a point here. But what is the most fantastic, I think, is the position velocity diagram. If you put the position velocity diagram around this axis, what you see is something which is completely symmetric. And what happens, and that you can see in the velocity field, which is there on the bottom left, is that really it's like a butterfly symmetry around the critical line, where you see one image of the galaxy in one direction, and then exactly symmetrical, like mirror symmetry, the other part of the galaxy. And so you have two at once. You have two rotational curves, and you can measure here the rotational curve of a galaxy at redshift 2.3, which is normally so weak that nobody could detect it if it were not amplified. So we're currently working on this and essentially looking at the characteristics of the clumps you see in this galaxy. There's another even more interesting serendipitous detection. I say more interesting because the guy who detected that was working on a completely different subject, which was looking for dust disks around young stars. And he was looking with the bolometer, and he found an incredibly strong source. And he didn't know what it was. It was so strong that it was impossible it could be an extended disk. And in fact, it turned out to be an incredibly interesting, bright 7-millimeter galaxy at redshift of 3.9. And so that was quite exciting. It was identified by searching with this broadband facility at the 30-meter for CO lines. You see that many CO lines were detected, including also neutral carbon here, which is going with the CO726 in one band. And so the derived first estimates of the gas mass and the luminosity, you see it's 10 to the 12, but that's the apparent luminosity because you have to correct for the amplification factor. And then this winter, we did an image of this with the Plateau de Bure with 0.115 arc seconds. And you see that's a really very nice Einstein ring. And I think that's a nice story because it's somebody who was absolutely not on the field, looking for completely different things, and now he's embarked in these high-Z studies. Let me now go back to the impact of Herschel. Not only does Herschel cover a very wide area, which was uncovered before, except for us with the South Pole telescope, but covering such a big area not only gives you many, many sources, but augments the likelihood to find lens sources. Because they are rare, and to find them you need to cover, unless you are lucky, you need to cover large areas. And that was predicted by Mathieu Negrello in 2007 and has been completely demonstrated with the current available data on Herschel, where when you do the number counts, you see that for the strongest, the most intense sources with the strongest flux, there is a real excess here above something, a flux density of hundreds or so. And in that box, in that area, indeed, the likelihood to find lens sources is the biggest. And so that was done with the first releases of the Herschel data, and it's a paper published in Science, where some of these sources were followed up with interferometers, including the SMA on Hawaii, but also the Plateau de Bure, and other instruments to not only determine the redshift of these sources, but also map them. And you see that indeed that is the dust emission, that the dust emission is sort of also like an Einstein ring or complicated, indicated that indeed we're dealing with lens sources. Those sources are all at redshift 2 or so, at 3. And with the magnification factor, which is still poorly known, it depends on the modeling of the foreground lensing galaxy. But typically, they're above 10 or so, 10 to 30, or up to 50 for the most extreme cases. This is just a snapshot of work we have done this winter following up on the Herschel sources. So we picked up about 7 or 8, I forgot, with Rob Iverson, to follow up in the molecular gas these objects and see what their real structure and morphology is. Those are, I think, two beauties. This upper one is Lockman 01. It's a source from the Hermes field, which was also measured with Karma. But with the Plateau de Bure, we achieved a much better angular resolution. And what you see is cloverleaf type of emission. Cloverleaf also has these 4 point source emission here. And it's really the deformation by the lens of the background source. The other source is even, I think, more interesting. It's called ID11. It's a redshift, I think, of 2.9 or so. And I think it's the first Einstein ring really discovered at millimeter wavelengths. What is interesting is that the shape of the line is pretty complex, and only the red part of it is completely amplified in an Einstein ring, and the blue part isn't. So we have a beauty there to be modeled and to understand what the background source is. The angular resolution of these things is about 0.59 seconds. Now, another interesting source is also a Herschel source. It's ID 141, which is, I think, still an exceptional source in the Atlas, even in the Herschel surveys, as it is one of the strongest sources ever measured at 500 microns. And it's a so-called 500-micron riser in the sense that, as you can see from the spectral energy distribution, here it's 250, and you see that you go to 350, 500, and still the spectrum is rising. So indicating right away that it could be a source at very high redshift. We measured it immediately after being aware of this source at the 30 meter with Mambo, and measured the 1 millimeter flux, and the 1 millimeter flux was 40 millijansky, or 38 or so, which is one of the strongest sources ever measured. And even that, I mean, constrained the photometric redshift, so based on simply the flux density, quite poorly. And with modeling, we were sure that the redshift was in between 3.3 and 4.2. So what I decided to do there as a sort of a example of what can be done with a sensitive instrument and a very wide band range, I used the interferometer this time to search for a CO line. And this is the first time that an interferometer is used to do the blind search of CO lines in a very wide range of redshifts. And so we did that last summer and did 5 settings. So the spectrum you see here, you're probably not specialists, but this is covering 20 gigahertz, which is quite amazing for an interferometer. It's done in 5 settings, each setting 20 minutes of observation. And unfortunately, we started this way, and so we had to do the 20 gigahertz. But there is the line. So we detected a very strong line. And then we suspected it was a CO403, and so we tuned to the other frequency, which was expected, and indeed found the other line, CO524. So you have 2 lines, and then that unambiguously gives you the redshift. And redshift is a redshift of 4.29. So following that, we measured other transitions which were available either at the Plateau de Bure or other instruments like APEX. And we measured 3 CO lines. We detected a C1 line, which is going with the CO76. And we measured a beautiful C plus line with APEX, very strong, 200 millijansky, with a complex profile. And so it really gives you in one go all sort of information, not only on the molecular gas, but also on the surface of the molecular gas, which is impacted by the UV field, and hence creating a photodissociation region. Those are the images. So we used low angular resolution because we were in compact modes. And we only have an upper limit on the size, actually, which is about 2 arc seconds or so. So it's a compact source. And we are currently this winter doing higher resolution observations to try to find out what the morphology of the source is. The properties of the source, so this is to the left a spectral energy distribution, the dust continuum, superimposed on the data obtained for MM82, a starburst, a local starburst. You see that there's a 1-to-1 correspondence. So very clearly, this is a starbursting galaxy at a very redshift, and with property luminosity, which is comparable to a little bit more than MED2. And to the right, then, again, the spectral energy distribution of the CO lines from which you can derive these physical quantities. And again, you see that the gas is very dense, 10 to the 4. It's very warm, about 40 K. And there's a lot of gas, about 10 to the 10 or so. Of course, it has to be corrected for the amplification. The C+, I told you about it before, is an interesting measure. This is a complicated plot, and essentially what it shows you is the ratio of the C+ luminosity over the infrared luminosity versus, on the bottom panel, versus the infrared luminosity. And it's a well-known fact that, as you can see, that if you go to very high luminosities, there seems to be a deficiency of C+ with respect to what you would expect on PDR models from the infrared luminosity. And the source ID 148 falls right in the middle here. You see that the recent detections of C+ in more and more sources gives a sort of a spread in the diagram, and it makes things more complicated. What is interesting is recently, based on Herschel data, there is a paper by Gracia Carpo and collaborators where they revisited this plot, which is shown here, for about a sample of 70 sources, local galaxies measured with Herschel. And they plotted this, but also this plot, where the axis is still C+ over far infrared, but the x-axis is a ratio of infrared luminosity over a mass in H2. And so what you see is that here there is a very clear trend of decreasing here, but with a sort of a break in the slope at a value of L center over mass of about 100 or so, or 80. And I will come back to that later. The bottom line is that what is believed is that ratio, there's a break in the properties of the molecular gas and the interstellar gas. And what is right of that broken line here is gas which is very dense, very hot, and forming stars very efficiently. And what is to the left is gas which is less dense, less hot, less warm, and forming stars less efficiently than the right one. In other words, to the right there are mergers, to the left there are not mergers. Let me now go and leave for a minute the CO emission. I talked about other molecular species. And as you know, as I said before, there are all sorts of other species. There are atoms, of course, but also other molecular species. For instance, water. And one of the very nice results of Herschel, and this is a FTS spiral spectrum, a complete spectrum from, 200 microns to 500 microns or so, of the very famous AGN, nearby AGN starburst, Markarian 231. It's a paper by Paul van der Werf. And what you see is that the spectrum contains a wealth of emission lines from not only all the CO transitions, but also from other species like water and like OH+, and like H2O+, or HF, even molecules which were never seen before. And this is a trace of a very strong activity driven probably by X-rays which are coming from the central AGN. So clearly, if such an object exists also in the high Z universe, water should be detected and quite easily. So that was done. That's another source of Herschel, ID17b, for which there was a broad spectrum taken over about 100 gigahertz or so. It's very low resolution. But what you can see is that there are all sort of significant lines here identified with the CO. So you see CO 7 to 6, 6 to 5, even 8 to 7. But also, interestingly, there was a line of H2O which was tentatively detected in that object. And so it was so tentative that we decided to follow that up with the Plateau de Bure using the new receiver. You see that the wavelength is about 290 gigahertz. And this is the detection, I think, much more clear than the other one, of water emission in a redshift 2.3 sub-millimetre galaxy. And I think it's the first robust detection of water in the early universe. During this winter, many other people tried to do it, and I think there are now 4 objects for which there is not only one line, but many lines of water in the early universe. So it again opens a complete new window. We're not doing only CO now, but water, and I think ALMA will play a very key role there, trying to probe all the water lines. I will go very quickly here. It's an example of a work at lower redshift, but at the point where the activity was the biggest, between 1 and 2. And it's one example of a large program, so just a little word here. at the 30-meter and the Plateau de Bure, it's possible to ask for very large programs. A large program being more than 100 hours or so. It can be up to 500 hours. And it's spread over many semesters, and it has been very, very successful. And I think all the programs which have been accepted have had a yield and publication rate which is quite fantastic. So that's a new scheme, and I just advocate it because as Spanish you can access the 30-meter and the Plateau de Bure. So here the goal of that program was to measure cold gas masses in normal high galaxies with trying to answer different questions. How galaxies obtained their baryonic mass, how did they convert into stars, and how they evolved into the population of local universe galaxies we know of today. So the total sample is about 25 or 30 galaxies. This is now done, and I will just show you a few results of this program. First of all, this is a map of one of those galaxies at a redshift of 1 or so, where in red you have the CO322 emission superimposed on an HST, or I think it's a VLT image. What you should note here is the wonderful CO rotation curve in that galaxy. It's not an amplified galaxy, it's a normal galaxy, and we have the sensitivity now to do rotation curves in CO, not only in H alpha. So one of the goals of this work was, first of all, to compare the dynamical masses, the baryonic mass and the CO, and so the gas, molecular gas fraction and of CO. And then you see here a plot which shows you that for typically for the galaxies we measured between 1 and 3 redshift, the fraction is about 0.3 or between 0.3 and 0.5 or so. The other interesting general result is that the famous Kennicutt-Schmidt law, which links the star formation rate with the surface gas density. So in other words, to see if there is such a relation locally, which is well known, you see that from this plot, and if you put all the measurements which are available to date, that there is indeed a very linear relation which continues even for very for systems with a lot of high surface density and at high redshift. And so it's a really universal law with a slope which is about 1.1 or so. What is interesting is that if you compare this between local galaxies and high Z galaxies, so there are all sort of tricky things, I won't enter into the details. You see that although the slopes are comparable, there is a shift, in fact, between the high Z merger galaxies and the normal galaxies. And this is linked, in fact, to what you saw before with the C+ plot, where you had a break at about a ratio of 100 in terms of solar luminosities over gas of mass. And that shift is also breaking at about the same number. So fundamentally, there is a change in the physical properties of the gas, whereby, probably because of merging, you have denser gas, and so you activate the star formation inside those galaxies. So let me go here. In the last 5 minutes or so, I will talk about the future of IRAM in the ALMA area. On top, you have the IRAM Plateau de Bure. On the bottom, it's not IRAM Plateau de Bure, but it's ALMA. But that was about a few months ago. So I think there are a couple of more antennas which have been put on the site now. So there is competition. It's still not exactly the same surface because we have 50-meter antennas and they have only 12. But, you know, they're going to 64. And so we have to compete. ALMA is doing science. I mean, there were test data, and this is an example of a source which was measured with Apex, I think, in C+, and measured with ALMA successfully. And I just want to make publicity for IRAM because that band was the IRAM receiver. I mean, IRAM is also making receivers for ALMA and producing the band 7, so the 350 gigahertz receiver. So let me outline the our view of what we can do at the 30-meter and the Plateau de Bure. The first remark I would like to say is that the combination of the 30-meter and the Plateau de Bure will remain unique. As you know, when you do interferometry, you're losing flux because you have not the zero spacing, and you resolve essentially the sources. And you can recuperate that flux by measuring with a single dish. And the single dish being 30 meter as opposed to 50 meters for the Plateau de Bure, you immediately recover what is called a zero spacing. And that combination is unique. It's used currently by everybody, and it's an incredibly good tool. So that combination will remain unique even in the ALMA area. For the 30 meter, I think the telescope will remain one of the best. We have to see what is happening in Mexico with the LMT, but it's still not going on. And there are many routes, ideas about improving the receivers, making broader band receivers, making very large bandwidth spectrometers covering not only 32 but 64 gigahertz, heterodyne cameras working both at 3 and 1 millimeter, but also a new field, wide field bolometer camera. And the idea currently is to have a bolometer camera operating simultaneously at 1 and 2 millimeters, which will enable to do all sorts of good science, in particular in the SZ effect, because that's exactly where the kink is. So that's currently under study, and we are probably going to use a very new technology, which is the NKIDS technology. So Plateau de Bure. It's very easy and with a mouse click to show what I mean. It's essentially doubling the number of antennas. So that's Photoshop, that's easy, and now we have to do it in reality. And so the project is called NOEMA for Northern Extended Millimeter Array. And the basic idea is to double the number of antennas, so to have 12, 15-meter antennas, to double the east-west baseline, that is possible, and add also stations to the south, so augmenting by a factor of 2 the spatial resolution. And most importantly also, to quadruple the RF bandwidth of the receivers, going to 32 gigahertz. And that's the crux, because that will, if you do that, then in 2SB in dual polarization, then you can show that with 12 antennas in those technologies, you can reach about a third of the ALMA line sensitivity and about half of the ALMA continuum sensitivity in the northern hemisphere for the windows which are also available for ALMA. And I think for a price which is less than a year operation of ALMA. So I think that's something you have to keep in mind. So that's easy to say now. It's more difficult to do that. Let me briefly go about what is interesting. First of all, the angular resolution. By doubling the baseline, you see that NOEMA will sort of cover an area between, what is currently available with CARMA, the SMA, and ALMA. So it's an intermediate sort of angular resolution. In terms of sensitivity, I told you that the NOEMA will allow to have sensitivities which are commensurable with ALMA. It's not 10 times less, but it's only a factor of a few. And most importantly, with many antennas, not only are you going faster, but you're also improving the so-called the beams, the side lobes, and the dynamical range. And this is shown here. You have more surface resolving power, and you have a side lobe suppression, which is bigger than a factor of 10 or so. So you go faster, and essentially you have better images. And this is shown here with the beam. On top, you have the current situation with the 6 antennas. On the bottom, you have the foreseen situation with 12 antennas. You see that the beam, indeed, is improved significantly. So this is the baseline for NOEMA. We have also other options. The first one will probably be put into the baseline. And the idea is to really take advantage fully of the capability to observe at millimeter wavelengths. So to go to very low frequencies up to 70 gigahertz, which are very essential for people doing galactic science, for instance, because they are deuterated species which are emitting at those low frequencies. And then having dichroic mirrors for full polarization dual band observations. What does that mean? It's simply that you're not observing with one band at the same time, but you're observing with 2 bands. And so you're gaining a factor of 2 in time, observing time. And then full phasing for the VLBI, that is something which will be done. And then for the very far future is to start to build not only one pixel receivers, but multi-pixel receivers. And that's very difficult because technically nobody has done it yet with an interferometer, but also it involves a very heavy colorator, as you can imagine. So, there are all sort of key science aspects for NOEMA. I will just mention 2. I mean, for the high Z universe, as you have seen, I'm convinced, and I hope you are also, that millimeter wavelengths are key to really probe the very high Z universe. If you look at redshifts of 10 or so, really into the ionization epoch, the C+ line is at 3 millimeter. It's not in the sub-millimeter bands. So I think it's very essential to have, in parallel to what ALMA is going to do, another instrument which is fully dedicated to do only work at 3, 2, and then when possible 1.8 millimeter. ALMA has been built at 5,000 meter. It has superb dishes, which have been very expensive, with fantastic surface accuracy, and that is done and aimed and geared to do 7-millimeter work and not work at 70 gigahertz. That's my point of view. There's also other things for the galactic work. As I said, I mean, the star formation takes place in very cold gas, whose cold gas emits in the millimeter and not in the sub-millimeter. There are also strategic aspects as well, and I just wanted to mention one, which I think is important. As you know, ALMA is an empty shell. I mean, everything is done not by ALMA, but by other laboratories, by IRAM, by Onsala, by Cambridge, by NRO, etc. So they really depend on healthy institutes producing, with people knowing what they do. And I think in the future, if you want to replace things on ALMA, upgrade instruments, Europe needs to have an institute or institutes which are capable of doing interest experiments. And I think IRAM needs to continue to exist, and to continue to exist with engineers of high clarity, we need to have ambitious projects to keep them. I think that's another point which is important. ALMA is also, I said before when I started, a giant, and it is really a giant. And so it goes slowly. And as you know, when ALMA is going to be operational, it will be a fantastic instrument, but it will operate with technology which is already 10 years old, like a space project. I think that institutes like IRAM have a much greater flexibility in reacting in time to new technology and testing it. I think ALMA will be very difficult to use for testing new IDs and new technologies. You first have to go to other instruments to do it and then implement it. And I think that IRAM will play there a key role. So, in a nutshell here for the IRAM in the ALMA area, the NOEMA project is feasible. I mean, if we do have the funds today, we can start immediately. I will come back to that. There's still a unique combination with 30-meter and NOEMA. And I think it will provide a very powerful array which is entirely dedicated to millimeter astronomy, where you can then, with the current instruments or the future instruments, cover from the ground with commensurable angular resolution and sensitivities the domains from the centimeter with the EVLA, that's the extended VLA array, NOEMA, the millimeter array, and then ALMA in the sub-millimeter range. And technically and financially, the risks are extremely low because everything is done in-house and we know exactly how to do it. So what is the state today of NOEMA? We are currently discussing with the partners to start the project. In January, I did send a request to the French government, and I was happy to hear that we got 10 million to start the project. And so the good thing is that the partners, the Germans, will co-finance at the same level. And so hopefully, I mean, in the next coming months, there will be a council meeting where we're going to announce that we start NOEMA officially and start to build it. And so hopefully the schedule, of course, is open. But what I hope is that in 2015 or so, or 16, we're going to have NOEMA operating. And the current idea is that the partners finance 4 more antennas and with the receivers and the correlator, and that we try to find other partners to find the additional money to do the 2 other antennas. So that's what I wanted to tell you, and thank you for your attention.
Does anyone have any questions for Pierre?
Just a simple question. What about the site conditions? Because, of course, ALMA needs it requires a very low, very high altitude, very low humidity, and so. But is Plateau de Bure comparable to the best places for doing millimeter astronomy side?
So the Plateau de Bure is, first of all, at an altitude of 300 meters, 500 meters. So it's a low side. It's twice lower than ALMA. And of course, we don't have the same conditions than ALMA. It's not sub-millimeter. It's sub-millimeter about 10% of the time. In the winter, as you've seen, we have done 350 gigahertz measurements. And that's really doable when there's low water vapor in the atmosphere and in the winter, 10% of the time. Otherwise, the Plateau de Bure is very good for 3 and 2 millimeters all around the year. That's not a problem. For 1 millimeter, it's more difficult. It's essentially winter frequency, but there are days in the summer or intermediate seasons where you can also do 1 millimeter. So clearly, it's not a sub-millimeter site, but it's an excellent millimeter site. It's comparable or even better than CARMA. It's, of course, not as good as Hawaii, but the SMA has only very small dishes, and as you know, politically, it's impossible to build new antennas there.
Well, I have two questions. One is related to the antenna at Pico Veleta.
Yeah.
You mentioned that you will see what happens when the Gran Telescopio Milimétrico at Mexico starts operation. It is about to start, should say. I would like to know which are the differences, which are the advantages or disadvantages of these two telescopes when the one in Mexico becomes in operation. And the second question had to do with the Kennicott-Smith law that you mentioned. Kennicott-Smith law, right? So I don't know if I understood well. You said that when you compare, I mean, Gensel and collaborators, when they compare this law for mergers and non-merging systems, they find that for mergers, the efficiency in transforming gas into stars is higher. And I just wanted you to tell us a little bit more.
So for the first question, I'm not that familiar with the Mexican telescope. I think I'm looking at Christophe Morisset because he's living in Mexico and he should know better than I do. But what I know is that, first of all, the schedule has slipped tremendously. And what I understand is that they're trying, I think, for this year to start with a surface of 30 meters and not 50. That being said, I mean, you should be aware that the 30 meter started 30 years ago, and it was a long road to the excellence we know today. I mean, I think it's only recently that people completely understand how the telescope moves and to really understand it as well as possible to improve and to use it as best as possible. So there will be a long, I think, time lag before the LNT is in full speed. That's my impression. In terms of instrumentation and whatever, it's clear that the LNT is going to come. It is a very good site. It is probably not as good as I understood. It's high, but it's very exposed. There's a lot of wind. I mean, it's not the prime site of ALMA, for instance. There are also problems with the panels, I've heard, so that has to be seen. But clearly there is, as you well know, there is a lot of instrumentation, which is superb. I mean, there's a large field camera, a bolometer camera. There are fantastic spectrometers. So clearly, I mean, the LNT is going to...
Will it be a good complement to the thing we already have at Pico Veleta?
If the LNT works as it should, it will be a competition, a direct competition. Yeah, that is clear. But we are not there yet. So the other question is, it's a very good one. It's also a complicated subject. I think I don't want to enter so much into the details, but as you know, one of the very key things in these studies is to know how you convert what you measure in CO, for instance, and the H2 gas. And there's a literature which I don't want to enter into here, but it's clear that that factor which is used, the alpha factor, is different for the mergers than for the local galaxies. And if you, and I can show that. If you would use the same factor for the merge, I mean for these high Z mergers, and then you come to conclusions which are at odds with what we know elsewhere. If you do it here, you see that everything comes on the same line. But then what you see is that you would expect for a given molecular gas, in fact, numbers for the mergers which are completely at odds in terms of star formation. And so it's still, it's an open issue, and I think it's quite interesting. The basic thing is that the slopes are the same. That is very clear. But there seems to be a sort of relation, a shift in the relation. And interesting enough, it's a shift you also see in that plot I showed you with the infrared over C+. And so everything tends to show that there is a difference in the physical conditions of the gas, which is, understandable, but it has to be quantified more.
How do you measure the gas? Yes. How do you measure the gas quantity in this project? So you measure the CO
So what
CO.
you measure, I mean, that's,
Yes,
that's a very
but
good.
you have to compare from the CO to H to molecular gas.
I mean, for the high Z galaxies, I didn't enter into the details here. But the high Z galaxies, you know, the higher the Z, the higher the CO lines, the translations they are, you measure, and even at millimeter. You measure not 1 to 0, but you measure 4 to 3, 5 to 4, and whatever. So you need to know what the excitation is, what the conditions are, how you go from that to the CO1 to 0, which...
Yeah, but the condition changes if you measure different lines.
So you make all sorts of things. You go from the high transitions to the CO1 to 0. They use a model, so if you have many you know, lines, you can, by modeling, expect what you would see in CO1 to 0. Sometimes you can measure it. It's difficult to do that with the DLA. And then you go from the CO1 to 0 to the H2. Because it's famous conversion, or infamous conversion factor. So there are lots of strings attached to it. And I think...
but at the end, for this plot, what you use is the derived molecular gas surface density at the end.
Yeah, that's what you use.
By using different methods for different lines.
Is the instrumentation at IRAM suitable for efficient follow-up of the Planck Sonyaev-Serdovich clusters of galaxies?
Yeah, that's what I mentioned very briefly. What you need is a bolometer working at 2 millimeters, and ideally to have one working at 2 frequencies. So what we are currently doing is to pushing for a project whereby the bolometer measures both at 1 millimeter and 2 millimeters. So there are many reasons to do that. I mean, the first reason is that it's interesting for the SZ effect. It's interesting for measuring spectral indices of dust in different regions. It is efficient because in the summer at 1 millimeter, the weather is not that good at the 30 meter, but you can still do 2 millimeter. The 2 millimeter window is very good. The transmission is always at 90% or so. And yeah, and for the SZ effect, I think that, for instance, Planck, you know, there's this wonderful catalog of clusters. And we already have started to measure with the 30 meter. But having such a machine will be wonderful.
Any more questions?
Yeah. That's the third one.
No, it's just a comment. I mean, you said that when the GTM becomes available and working properly, they will become competitors. And just would like to comment that would be very good, because to get a certain time at picobellata is quite hard. So it's not bad to have more facilities to do work like this, because...
No, I'm always, I mean, you know, it's simply, I mean, ALMA is also very good. I mean, it boosted everything, and but it's a competitor still, and you have to, as a director, sort of think about what shall I do.
Okay, can we thank the speaker one last time? And there's a coffee break at the canteen now after the talks.